Good morning. So today I wanted to do examples related to module 5, which is numerical differentiation and integration. But before I do that, I wanted to also share with you some updates about the remaining part of the remaining deliverables in the course. I have been constantly running out of time for each topic, and I figured what could be the reason. And these quizzes that take 40 minutes, I think I misjudged the amount of time I should have been giving you. Maybe 20 minutes would have made it more competitive. But now I'm not going to change it back. But what I wish to do is make quiz 5 and quiz 6 like an offline quiz, something you can do on your own pace at your own time and upload it via Canvas. Okay, so it's going to be using Excel or MATLAB, it's your choice, but you are going to still solve two problems using Excel and then write up the solution, upload to your Excel file, and I'm going to grade both your handwritten work as well as the Excel file. Okay, except doing this in 40 minutes, you're going to get like 3 or 4 days to do this. 3 or 4 days for two problems, that's it. Okay. You would also still do your homework problem, which is like one problem per module, which is a kind of a lengthy problem at the end of the exercise. So you would still do that as well. This will free up 40 minutes for me to use for problem solving. Okay. So that said, today I want to spend the time doing examples related to module 5, and I will post the quiz after today's lecture, which will be due by at the start of the next class on Tuesday of next week. That quiz will be due. On the same day, your homework 4 is also due, which I'm sure you have been working on, the regression and interpolation exercise. And on that day, we'll start module 6, which is the final one. So next week, I'll do module 6. The week of Thanksgiving, I'll wrap up module 6, which will complete the course topics. Okay. And when you come back after Thanksgiving, we'll have the exam on the very last lecture on Tuesday, December 3rd. The quiz 6 and homework 6 will be due the next day. Okay, so by the last working day, that is the last day of classes, Wednesday, you'll be done with all of your deliverables for this class. And I will grade all of them. And by the end of study day, that is December 5th, I'll upload all your scores so that you can see it and decide if you want to take the optional final or not. Okay. Regarding optional final, I haven't checked on which day it falls as per the time slot for this class. I'm going to be out of town, so I'm going to arrange a proctor to come and administer the exam. I do want to ask you, would a take-home exam be of something interest to the class, or you would prefer coming in for 120 minutes and taking a conventional paper-based exam? What would be, yeah? Take home, you prefer that?
Because I have finals on my other classes and I study. And I feel like I have to study this one on top of all of them.
It would be difficult, like it more stressful. Okay. If it is a take home, which I am fine with, it would not just be like pencil and paper. It would also be, involve you doing some calculations on Excel. Basically, I can make an exam in which all 6 problems are Excel based, and you would upload a single file with problem like tabs P1, P2, P3, P4, P6. And that's it. I look at your numbers, I look at your formulas, methods, and just do the grading. So would that be something you would be willing to try? You don't have to, you might have to write minimally, so you could attach like a Word file or a handwritten PDF copy that will support your calculations. But I'll see the calculations, I'll see your notes and grade it. Instead of doing it in an exam where you do only pencil and paper and calculator, you can do Excel and pencil and paper. Would that be okay for you guys? So if I post it, let's say on by the end of study day, I'll post all your scores. The following day on Friday, I'll post the exam and give you 3 days, or if you prefer, I'll give you 4 or 5 days, even whatever, we can talk about it. And it will be due 3 days, 4 days later. Question?
Is the exam 2 the final exam?
Exam 2 is like part of the course, which is compulsory for everyone. I'm talking about the optional final. So the optional final, if I make it take home, would that be a favorable thing for you? Yes?
Yes.
You're all very honorable people. You won't cheat. You won't talk to your friends or go on the internet. I trust you won't do any of that. Okay? All right, good. So that said, today I want to discuss these examples on module 5, which means I get 3 full lectures to discuss module 6, which is by far the most important topic of this class. So I wanted to give it enough time. Okay. So let's talk about this. So here is a data set, okay, which we got in the laboratory. So take a listen. If you can download this file, keep it ready. But for a moment, look up and listen to me. This is a signal that we measured using an oscilloscope, and what we have provided here is the time versus voltage profile. So if I take all the data and plot it, here's a signal that looks like this. It's basically some kind of a sine wave or a periodic signal that we got, and I have provided the raw data for you. This is like a lot of data points, somewhere I think maybe like 10,000 data points or something, 16,000 data points. So there is around 16,000 data points, and we are going to take a subset of this. So if you go to the tab called class activity, I have selected a subset which is about 113 data points. Oops, which is about 113 data points, and we are going to do some calculations using this data. So if I plot it, what am I getting? Time versus voltage. Here is my data. Okay. We talked about calculating derivatives using approximations, right? Last lecture, those who were here. So what I want to do is to take this data, which looks very choppy. It looks like a sinusoid, but not enough resolution. I want to use numerical methods to compute the slope at a given point. That's with various orders of approximations. Okay, do you recall from last time we talked about first order approximation, second order approximation? We want to use a formula, at least understand how to use them, get an answer, and try to use a better formula, and so on. Okay, so shall we get started? I'll guide you through this, okay? And I also have a mock quiz posted. So after today's lecture, I'm going to repost this file with the actual quiz, which is in the next tab here, quiz 5 P1 and quiz 5 P2. So quiz 5 for the quiz first problem is going to be numerical integration, where we will evaluate an integral that looks like this. Look at the question. Evaluate the following integral numerically using Simpson's 1/3 rule. Choose the number of segments n such that the difference between the numerical value and exact value is less than 0.1%. So this is the question you are going to face as part of the quiz, or this mock, but something like this. Shall we start with this? Okay. So before you start, you need to know what is I exact. You need to evaluate this thing analytically, and keep the answer ready, which we will do. But since we are here, let's start with the implementation of Simpson's rule. So what is Simpson's rule? Do you recall? So I'll draw the figure here. Here, maybe throw on the light. So I have okay. So Simpson's 1/3 rule. I equal to 1/3 b minus a divided by n f of x naught plus f in is it 4 times? 4 times the odds. 4 times I equal 1, 3, 5 up to n minus 1 f of xi plus 2 times j equals 2, 4, 6, and so on up to n minus 2, f of xj, and then f of xn. So how you would remember this is to say here is x naught equal to a, here is xn equal to b, and you have x1, x2, xn minus 1, xn minus 2, xn minus 1, and so on. Remember that n must be even. And xi, any xi is equal to x naught plus I times b minus a divided by n. This is the formula you need to get started for Simpson's 1/3 rule. We are going to implement this formula on Excel, or if you want, you can do it on MATLAB as well, if you know how to do. Okay, it's not a big stretch. So step 1, I would say, I'll write the steps here. Step 1, you don't have to write this. I'll write and you can see the annotations later. Step 1, generate a set of x values by segmenting the interval a to b. So that is what I mean by generate xi values. Okay, using the formula xi equal to x naught plus I times b minus a divided by n. So I'm going to write I, okay, I'll write it maybe somewhere here. I xi, and then I have f of xi. Write it here. I'll make it a little prominent. I xi f of xi. What is I? If I is 0, xi is a, which is in this case a is 0. So I'll write here a, b. A is 0 and b is pi by 2. Can you see properly? Is the font okay? Okay. So then I'll choose n. Okay, I have to choose n value. And the problem doesn't give you an n value. It doesn't say use n equals 10. It says choose a value which will get you a certain degree of accuracy. So we'll have to do some trial and error. We don't know the answer or what value of n to use. Let's start with something like 10. 10. So your I starts at 0 and goes by increments of 1 and goes up to 10. So your I values are all generated. Okay. And you want to compute what is b minus a divided by n, which is pi by 2 minus 0 divided by n. Or the length of each segment is 0.1571 to say to 4 degrees, the 4 digits of accuracy. Question?
Yeah, oh, there it is. I just wanted to see where you got the B.
The b is the upper limit.
Okay,
A to b.
yeah.
A to b. B is upper limit. A is the lower limit. I'm building the sheet such that you can use this for any problem. Maybe if you're smart, also for your quiz. All right. So then I need to generate the values of the xi values. The first value is always equal to a. Okay, and the next value is x naught I'll put a dollar sign to lock it, plus I times the width b minus a divided by n, which I'll lock. So I get this set of x values. And as you can see, the last value should agree with b. If you do it right, xn, last value xn should be equal to b. Because x naught is a, xn is b. Okay, and your function is the function you're trying to integrate is e power minus x sine of 3x. That's what is given to you. So you just have to write exponent of minus x times sine of 3 times x. Evaluate that and populate the values. See so far? Parker, doing okay? Shall we do the next step? We are okay? Wyatt? Okay. All right, so next step is really simple. It is to implement this formula. It is to pick out the odds, sum them up, pick out the evens, sum them up, and then write down this formula. Okay. So instead of, I mean, if you want to do it on Excel, it's inconvenient to pick out the odds and evens. But if you look at this formula, this is a summation. Look up. This is a summation. F of x naught is multiplied by 1. All the odds are multiplied by 4. All the evens are multiplied by 2. All the last value is multiplied by 1. You can view the 1, 4, 2, and 1 as weightages. So we'll call them W of I. That is, they are the weightages for each value. And the weightage, you can summarize it using a rule. Can you? What is the rule for this weightage? If I is 0 or n, it is equal to 1. For the first and last value, I is equal to, the weightage is equal to 1. And for odd values, it is equal to, for odd values, you should multiply the odd value by what number? 4. So how will you state it as a rule? If this cell is odd, how do you check for odd numbers? I know we have to check, but I don't know how to check. So I will go here and check for odd numbers. Is odd. So there's a function called is odd. Returns true if the number is odd and returns false if the number is even. Perfect. This is what we need, don't we? We need a function that returns true if this number 1 is odd, or false if the number 1 is even. So we are going to write the weightage at the second line is equal to is odd. That's the name of the function, and we are going to write 1. So it's going to say true. Okay, and I can just drag that and put it across here. I knew what I wanted. I went to help and typed it and found it. That's how you should think about using programming. You can't possibly memorize everything. My wife will agree with me on that. All right. Now what? The weightages, this is just true or false, right? This is not weightages. So I'll move the weightages to the next cell and say this is 1. Last value is also 1. What is my rule here? If the adjacent cell is true, I need a weightage of 4. If the adjacent cell is false, I need a weightage of 2. Right? So you can write as a if statement, if the logical test equal to true, then the weightage is 4, otherwise 2. Check this out. I'm getting this cell to be 4, this cell to be 2 as odd and even. Okay, I kind of maybe went quickly, so I'll give you a minute to do this and get up to here. Then we'll proceed. Yes. Yes, tell me.
Can you show me how to do the function,
Which function?
just the function of x of I?
1 second.
I'm having a hard time putting it in the x.
Sure. Come again, which function?
X of I.
F of x of I. It's the exponent of minus x times sine of 3x. Oh, I didn't show you the function, it's in this corner. This is the integral. Okay. Is everybody up to here, the true and the weightages? You need some help? The true part?
No, I'm still doing that. Thanks.
Okay. Who's xi? Xi, sorry. How the formula for xi?
Yeah.
That is this formula is x naught plus I times the step length. It is x naught, which is the first line, freeze it plus I times whatever I is, the width, which is the b minus a divided by. Once you put it in, just drag it down. Yes.
So when you get x of I and f of x of I, what do you do next to get to? Right now, all my columns are the same number.
Okay.
So
The is odd. Okay.
no, I'm saying, like, all of my, I haven't changed anything. It's just all the same. I don't
Okay.
do that for 1 year.
Oh, go to your Excel. So this is, what is that, 21? 21. So you are 21. Okay, go to the next one. D20. Yeah, okay, that is supposing. Yeah. Then this is equal to, then T21 plus F21, F22. F22, it should be multiplied by the current IU. Can you change it to F22?
Yeah.
And then drag it down. It should update with each row. F21, F22, 23, 24. You getting this thing?
Yeah.
Just start over, okay? First line you write equal to A, whatever A is. The second line you write A, that is X naught plus the delta times I. One second. Okay, same problem. So what you need to do is, what is the formula for Xi? X naught plus I times the width. Implements that. X naught is always the first line equal to A, the starting. So this one is just equal to the starting point, A. That's where scroll up, your A would be
I
equal to.
E minus A.
Yeah, enter. Second line is equal to whatever X naught is. Click, please step plus.
Yeah.
Just put $2. Dollar three, dollar
Just
three.
a function. Function,
Okay.
so it's exponential. -3.
Plus I is this column here, A21. Yep. Times this one. Yeah. And you need to freeze it, $T, $70. Enter. Now drag it down. There you go. So then you're basically, you need to do the weightages column. The good
Show F.
f of xi, exponent of minus x. Oh, you want to see the function. Okay now?
He just got in this. I times the B minus A.
Yeah, that's just because A happens to be 0. Yeah, the first one, the x naught happens to be 0. So this program will work for this problem, but if I make A non-zero, it won't.
Yeah, how do you go when you're? Yeah, I'll set the 0 back up to being 0, but when I do my drag, it'll follow this drag down.
You need to freeze your value of B minus A by N. That is, if you're doing that, you need to put the double dollar sign.
Double dollar sign.
Yeah, F4.
Okay.
The weight is based on a rule that if it's the first and last, it's just 1. If the ISORT column is true, then it is 4. If it is false, I make a rule.
This is the weightages. Just How do you do the wages? Or do you-
Here's the rule. If it is odd, so what I did here is not manually enter this. I say if the is odd column is true, make it 4. If it is false or otherwise, make it 2. True means 4, otherwise 2. So if you look here, here's the syntax. At the top here, there's the syntax for the weightage. Are you able to get the weightages, everyone? Are you able to get up to the weightages?
Working on the new.
Could I see that, the true function again? I'm sorry.
Yeah, true. Yeah, sure. Yeah. If the column J is true, the weightage is 4, otherwise it's 2. The first and last entry I just manually entered as 1. This is 1/3 rule, right? What is the difference between 1/3 rule and the trapezoidal rule as far as the weightage is concerned?
Trapezoid rule. Like differ between odds and evens, right?
It's just 2 for everything that is not 0 or 1, except the endpoints, everything in the middle is 2. So it's just like throwing a switch. If in this column Wi, if you just instead of writing 4, 2, if you write 2, 2, you end up with trapezoidal rule. Just one switch.
Why don't you do anything for the last, for number 10?
Say it again.
Why don't you do any, true or false, or you change it to 1 for the last, the number 10 line?
Yeah, I just entered it manually.
Why don't you do the, like, the weightage for that one?
Because then it will show a weightage of 4, whereas in theory, the weightage is 1, not 4. So the first and last point don't conform into this pattern. No, when we went through the derivation, we saw how this came about. Yeah, if you go back 2 lectures, I explained why we segment that into trapezia. The first point is used by only 1 trapezium, whereas the midpoints are all used by 2 trapezia. And the last point also used by only 1 trapezium. That's why they don't get counted twice. So they don't fit within this pattern. Okay, where are we? Where are you guys? Are you able to get the weightages? Are you able to multiply the weightage with the function? Yes?
When I multiplied the weights with the function, I got a different number than you want to sum it. Let me just change, never mind. It was positive, I changed.
Okay. Yeah.
What did you find,
Okay. So are you up to here? You have the sum? Everybody has the sum? Right?
I'm having trouble with my if. I have to do it the same way, but it's giving me like an error.
For this one?
Yeah,
Just for now,
Yeah.
enter it manually.
Yeah.
Enter it manually, later you can figure it out from the Excel sheet. So does everybody have the sum with them? Are you up to here? Maybe? Okay. So now look at this formula. It is 1/3 the width multiplied by the summation. The sum is this summation. This summation right here is the sum. Okay. So I have to take 1/3 multiplied by the width times the summation. If you do that, you're going to get 0.32083, which we don't know whether it's correct or not, right? We have to check it against the analytic value. You have to check it against the analytic value. So let's compute that also, the analytic value for this integral. So if I have, you can do this on your notebook and just tell me the answer, because we don't want to spend too much time on this. Remember, the goal of the exercise is to just get the analytic value, not, this is not the main question. I'll rewrite it somewhere. Okay, it's a little bit difficult to read here. I'm almost done. So let me compute this. So, okay, good. So I think the I exact value is 0.404068. Is anybody getting different values? If I didn't make any mistake on the board here, I think I'm right. So for the moment, let's consider this to be correct. I could have made mistakes, but I don't think right now. But let's just say we assume it's right. The exact answer is 0.40 something. The value you get using trapezoidal rule is 0.32083. How will you assess the error? Error would be 1 minus the numerical answer divided by the exact answer expressed as a percentage. That's 21% error. It's 21% error. Okay. So now your goal is to choose a value of n such that the error value comes down. Right? So you did 10, you're getting 20%. This is like bisection. Maybe you choose 100, you would be very close, or maybe even overshoot it. Then you can come back or just leave it at 100. Because the problems usually say the error is less than 0.1%. It doesn't say error has to be 0.1. It can be even much less than 0.1. Okay. With me so far? Yeah?
So you said you can overshoot the error,
Yeah.
right? So if you did like 1,000.
You would always get a good answer probably.
Yeah,
That is okay. If you just like blindly do it, you're just wasting computing power
yeah.
and number of operations. You're just doing more operations than necessary.
So what you're after is just to 1 decimal point, like less than
Yeah.
1. So because if you did 1,000, it would be 0.0000 or something like that, like.
Yeah. Yeah. Maybe I can word the question saying choose the value of n that is the minimum value that gets you within 0.1%. In that case, you can't just do 1,000 and leave it. All right. So now you have all this, right? How will you now change the value of n so that you can try different value and see if your answer gets better? Did this make sense so far? You have a question?
How did you get I trap?
ITRAP is the formula is basically 1/2 b minus a divided by n, and w of xi is 1 and 2. That's it.
It's the same thing, just 1/2.
Yeah, 1/2. The formula, if you look it up, it will have 1/2 instead of 1/3. Yeah.
You just change the xi.
You don't even have to change the xi. If you're doing trapezoidal rule, you can use any value of n, no constraint. Only Simpson's rule has the constraint, n must be even. You can do 9 or 5, it's still okay for trapezoidal rule. Okay, so I'm going to stop this problem here. Let you figure out later how will you vary n, because that is your quiz. You'll have some challenge left. Okay. Is everybody kind of here at this point? You're able to get the I 1/3. Okay. All right, good. So this will be posted. The mock quiz with the solution, I'll post it on Canvas. Okay. Now let's do the second problem. Evaluate the slope. So here is a bunch of data. X and y of x. Okay. and if you plot it, it's going to be a messy function. What I'm asking you is to get the slope at time, at x equal to 3.20 using a forward difference approximation for the slope. Now, to recap, you can derive approximations for the first derivative, second derivative, any derivative. And how you would do that, I went over last lecture. You don't have to do this for every type of derivative. You go to chapter 22. If you have your book with you, chapter 22. I'm sorry, chapter 23. The section we discussed last lecture was 23.1. High accuracy differentiation formulas. That's what we discussed. Table or figure 23.1, 23.2, 23.3 is basically the resource you need to use in the quiz or the exam. If I say forward difference approximation with second order accuracy for the slope or the first derivative, first look up forward difference approximation. That is figure 23.1. I want the slope, which means the first derivative. And I want second order accuracy, which means I'm going to be looking at who has the book with you? No one has the book. Open your book. You read it out to me so that I can understand at least one person knows or follows what I'm talking about.
What do you want?
I want you to read out the formula for slope or first derivative using forward differencing with second order accuracy. Six five six.
The second derivative?
First derivative, second order accuracy. This is going to be bad. I'm telling you, on Tuesday when you take the quiz or the exam, you guys are going to struggle. You have no idea what I'm talking about. Yeah.
F prime of xi.
Yep.
To negative f times xi plus 2.
Plus 4 times f xi plus 1 minus 3 times f xi. So I'm referring to these three tables in page 656 and 657. You need to be able to read those tables correctly. Okay. So I'm going to write, thank you, Santiago. So I'm going to write from figure 23.1, page 656, f dashed of xi equal to minus, what was it, minus 4 times? Minus f of x I plus 2 minus 4 times f of xi plus 3 times f of x, plus 4 times f of x I plus 1 and 3 times f of xi. The whole thing divided by 2 times h or 2 times h. H is basically step width. Let me write it here. Is this okay? Are we done with integration? Can I erase it? All right, so here's a quick primer. Listen up. Okay, so let's say we have data points. We have I plus 1, we have I plus 2. We can also have I minus 1 and I minus 2. I'm asking for the slope or the first derivative. That is the quantity I'm looking to compute. Slope or first derivative. I want forward differencing. That is told in the problem that I needed a forward differencing approximation, which means I have to consider I and to the right of it. With me so far? And I also want second order in accuracy. If you want only first order in accuracy, it will involve only 2 points. It will only involve 1 point upstream and the point itself. If you want second order accuracy, it's going to involve 3 points. So from figure 23.1, page 656, f dash of xi equal to minus f of xi plus 2 plus 4 times f of xi plus 1 minus 3 times f of xi divided by 2 times h. This distance between I and I minus 1 or between any 2 points, that is h. Step with me. Okay. So what you got to do is, if I want the slope at 3.20, that 3.20 point becomes your I. The next point is I plus 1 and the next point is I plus 2. You would have to implement this formula at I to get the slope at I. Okay. So let's identify where is 3.20 in the table. Here is 3.20. Okay. So we'll make it bigger and we'll call it I, which means the next 2 points are of interest to us. They'll be I plus 1 and I plus 2. Yes, question? No? Okay, so we want to compute. So this will be xi plus 1, xi plus 2. This is what f of xi plus xi, f of xi plus 1, f of xi plus 2. So if I want the slope or f dash of xi using the chosen formula, I would write this is equal to minus the I plus 2 value plus 4 times the I plus 1 value minus 3 times the I value divided by 2 times the separation between them, which I haven't done the computation beforehand. I'll just say it is in this cell. So step length is, you can check this in this data set, it happens to be a constant. So this is our slope using a second order accuracy formula and forward differencing. Okay. So usually the instance when you use numerical differentiation techniques is your data is not something that you know as a function. You just know it as a bunch of data points. That's when you use these formulas. Okay. So now get me the slope using a forward differencing formula that is only first order in accuracy. So get me the slope with a first order accuracy formula. Right, just say first order in accuracy. What would be the formula? F dash of xi is f of xi plus 1 minus f of xi divided by h. It's the formula in the preceding line in the figure, in the table. For your exam, for your quiz, you have to be able to read these tables. Okay, I'll give out them in the question sheet like a handout. If you can't read them, it'll be difficult. Okay, so slope using the chosen formula, which is second order in accuracy. Now I want to compute the slope using the chosen first order accuracy formula. Which would, so first order accuracy will involve only I and I plus 1, right? So this will be Fi plus 1 minus Fi divided by step length. So the slope estimates are vastly different depending on what accuracy you're using. When it comes to integration, when you go from n equals 10 to n equals 50 to 100, that agreement will smoothly decrease or smoothly increase. Differentiation can be a wild card, like one approximation with only 2 points gets you 300, and then one with only with 3 points gets you something totally different. Okay, so you have to be careful about this. So we did slope, first order, second order accuracy using forward differencing. Now let's do curvature, second derivative using, instead of forward differencing, let's do central differencing. So now we are going to do second derivative using central differencing and second order accuracy. Okay. You understand that we are going for a different calculation now, different quantity, which is like a second derivative. So this data is actually in the lab. We ran a voltage sensor or an ultrasonic transducer and got the output voltage. So the first derivative, second derivative could mean something, or it could be like a displacement. First derivative is velocity, second derivative is acceleration. Could be that. Okay. So now let's compute. Let's take some other point. Yeah, let's say we take this point 4, and at this point, we want to get the second derivative using central differencing approximation. Before you do that, can you, those who can, look at the sheet and tell us what is the formula for second derivative with second order accuracy? So this will be central differencing. So the table you need to look is 23.3, which is in page 657. Okay. F double dash of xi equal to f xi plus 1 minus 2 times f xi plus f xi minus 1 divided by h squared. Is that correct?
Yes.
Okay, that's correct. So this is your formula. This is your I. You call this I. The previous point is involved I minus 1 and the next point is involved which is I plus 1. Okay. So now you want to compute the curvature or the second derivative at x equal to 4.00. That's what you're trying to compute. And this is the central differencing second order accuracy. Central differencing second order accuracy, the formula is right here. So I'll write this is equal to fi plus 1 minus 2 times fi plus fi minus 1 divided by my step, which I'll put here, squared. And my step is any value, this minus the previous. So here is my curvature, which is 5,000 units. 5,000 units. Same quantity. We are going to calculate the same curvature using central differencing, but now we'll choose a formula that is higher accuracy. Let's do fourth order accuracy. So central differencing, fourth order accuracy. So this second order, I'm replacing it with fourth order. You don't have to look at derive anything. Look at the same table 23.3 and pick out the formula for me.
Say,
Fourth order.
f of xi plus 2 minus 4 f of xi plus 1 plus 6 f of xi minus 4 f of xi minus 1 plus
Which table are you looking?
23.3.
23.3. Which line? Third line or fourth line? Or
The fourth derivative.
I didn't ask for fourth derivative. I asked for second derivative.
And it's the equation.
That is line 4 minus fi plus 2 plus 16fi plus 1 minus 30fi plus 16fi minus 1 minus fi minus 2. That's your formula. Would make more sense if you had the book in front of you. So this is minus fi plus 2 minus fi plus 2 plus 16fi plus 1 minus 30fi plus 16fi minus 1 minus fi minus 2 divided by 12h squared. So this formula involves from I minus 2 to I plus 2. It involves 5 points. Okay, so we'll write I minus 2 and I plus 2 okay, so I want to get the slope here using this updated formula, okay, which will be, I just have to punch this in, minus fi minus 2 plus 16 times fi plus 1 minus 30 times fi plus 16 times I minus 2, I plus, I'm sorry, I think I'm going backwards, but it wouldn't matter because the sign is still the same, minus 336 divided by 12 h squared. Look at this. So the slope estimate using the fourth order formula gets me 6,400, but the second order formula gets me 5,000. This sort of major difference is common whenever your data is very noisy. If you had very smooth data, both these formulas would nearly give you the same thing. Even then, if you take an exponential curve, okay, if you take a curve, let's say you take this exponential curve, if you measure the slope or the derivative at this section where it is rapidly increasing, it matters whether you take only 2 neighbors or 4 neighbors. Because just 2 neighbors to the right has an enormously larger value than 2 neighbors to the left. Okay, so for functions that are steeply changing, rapidly changing, that calculating derivative and basically first order, second order derivatives can be a very tricky business. You'll have to try formulas of increasing order of accuracy to see until when that it actually gets you some kind of convergence. Okay. So as you can see, this is the other mock question in the quiz. That is, question 1 is going to give you an integral and ask you to use some kind of formula, either Simpson's rule or 1/3 rule, and you will have to choose n or do some tricky thing. Okay. This is more like a function is given to you. Problem 2 is a data set is given to you and you are asked to pick out a formula for the slope or curvature or some derivative, and you should be able to read the table 23.123, pick out the formula, implement it on Excel. Now, shall we do one exercise? That is, I have the time versus voltage. Okay, this is the class activity I planned today. Here is voltage versus time. I can plot this. It will be a choppy data. I want to plot the slope of this curve. It's like saying you get position versus time. From that, I want you to calculate instantaneous velocity at every instant and then plot that velocity. And then we'll also do the same for instantaneous acceleration. Okay, so it's like if I get you the speedometer data, you are asked to check at different times how fast is this vehicle been accelerating. Is the velocity changing rapidly or slowly? That's the kind of calculation we are doing. Are we all okay with this? I'll give you time to maybe finish up some loose ends and then we can proceed. I have exactly 15 minutes. Yeah.
You can post that one.
Of course I will.
Yeah.
Of course I'm posting all this. I don't know if I told you this story. Last fall I had one student who complained that I post all my mocks and even the solution. I once told this is the problem that's going to come on Tuesday, and still half the class bombed it. And that student was like, "You are making my score uncompetitive. Everybody is now going to get a full score." I said, "You wait and watch. People will still mess this up, and they know how to do this." So this sheet will be there. Are we good? Can we quickly plot? So this is voltage. I'll call it V of t. Next step, I want to calculate what is V dashed of t. Okay, V dashed of t. This is a time domain problem. So we will use backward difference. Why I told you, because anything that happens in time, only the past can influence it. The future doesn't exist, right? So I want to use. So the goal is to calculate the first and second derivatives with respect to time at each point. Okay, we won't worry about the first point. Okay, we'll start with backward differencing, first order accuracy for slope, and then second derivative, or I'll call this v dashed and v double dashed. So slope, we want to do second derivative, sorry, first derivative with backward differencing. First order accuracy. What is the form? What is the formula? dv or v dashed of ti is v of ti minus v of ti minus 1 divided by delta t. One step back, right? So I'm going to write, I'll start from the second line. This is the current value minus previous value divided by step length. I just want to make sure I get the step length right. Oh, okay. Current value minus previous value divided by step length. My step length except is been wrongly updated. All right, minus 250. And I can just drag this all the way to the last row and it would be fine, wouldn't it? Why would it be fine? Because when I move from this point, which is I, if I move to the next point, it becomes I and the previous point becomes I minus 1. So I'm just moving. So when I'm at I, I'm looking at I minus 1. When I move over here, I'll call this I and look at I minus 1 all the time. So the formula is the same. I just copied the formula to every cell below. Okay. So first step is we will want to plot. We want to plot these two quantities. Maybe we'll plot them separately. Let's plot. Take a listen. I just want to make a short point here. So this curve here, the lower line is the original value of the function. The higher values are the slopes. Because slope is a rate, it is numerically larger than the function itself. Because it's by delta t is a small number. So to make sure we can see both of them, we'll choose this and say format data series. We'll plot it as a secondary axis. So that if you want to read the values for the blue curve, you will read to the left. For the other curve, I'm slightly colorblind, so I won't say what color this is. For the other color, you read to the right. I've been having this for almost my entire life. I can't tell you what color this is.
What color do you think it is?
Orange?
Yeah.
Okay. It's a good day. Okay. So I have the two quantities, the original function and the slope calculated using first order accuracy formula. Now let's do the same slope, okay? So this is the slope with first order accuracy and backward differencing. We'll do the same quantity with only difference second order accuracy and backward differencing. Second order accuracy and backward difference. So if I want second order accuracy, B dashed of Ti, second order accuracy backward differencing would be 3 times V of Ti minus 4 times V of Ti minus 1 plus V of Ti minus 2 divided by 2 delta T. 2 delta T. You can't start your calculation at the first row, obviously. You cannot start it at the second row either. So you will start it only at the third row because you need 2 points, right? So third row, you will write equal to 3 times the function at I minus 4 times the function at I minus 1. I'm sorry, equal to 3 times the function at I minus 4 times the function at I minus 1 plus the function at I minus 2 divided by 2 times the step length. So if column C is your displacement, column D is your speed, and column E is also your speed, but with a different level of approximation. Okay. We are not going to go for higher and higher order of accuracy, but if as you increase the order of accuracy, at some point it will start converging. Like if you do 4th and 6th or 4th and 8th, you might not find much difference. Okay, but 8 means it involves 8 points in the past. Like looking back and taking the last 8 points to calculate the slope at the current time. Okay. So this sort of work is going to be very consequential for you, especially when you have experimental data and the quantity that you are seeking is not the data itself, but some derivative of the data. Could be that you are interested in the voltage, but it turns out voltage, the rate of change of voltage is what you really care about. Or current, it's not the current, it's the di dt that you care about. Okay. All right. And I assume that if I tell you instead of first derivative, get me second derivative with different accuracy, you can now do this. It's all permutation combination. Last thing before I let you go today. How will you evaluate the area under this curve? Say, for example, we are interested in this data, P of t, which is plotted here. I want to know the area under the curve. How it is defined? Integral from the first point to the last point of the function. Well, we don't know the function. We only know the data. So I want you to apply a trapezoidal rule for this data for which you know the function values, because all you need for trapezoidal rule or any numerical integration procedure is the value of the function. You don't care what the function actually is. Right? So so again, area under the curve is also an important calculation often. So I want to know area under the curve, and if I'm going to use the trapezoidal rule, I'll write this is 1/2 b minus a divided by n multiplied by summation I equal to 0 to n wxi f of xi, where the weightage is as we saw before, equal to 1 if I equal to 0 or n and 2 otherwise. Okay, so sorry if it feels a little bit rushed today, but I'm going to implement this calculation. So if I say what is my weightage, W of Ti, the rule is simple. For the first point, it's 1, and then it's 2, and except the last point, which is again 1. Okay, so W I've implemented as 1s and 2s. And then next step would be W of Ti times V of Ti. Multiply the function with the weightage. So weightage times the function, and I'm going to drag it all the way down. So weightage times function. What's the next step? Will be to get the sum, right? Get the sum first. So sum is equal to sum of this column 616, and then I trapezoidal rule is going to be 1/2 times the step length. What is the step length? I have it up here. 0.08, okay, times the sum. So the area under the curve is minus 24.64. Because that function, if you notice, that function has values that are both above and below 0. Some of those values will cancel out. Okay, so this will be like saying what is the time average value of that signal over the period that we took data. Okay, now suppose, last thing for the day, promise. Suppose I ask you I equal to A to B, not f of xi di, the magnitude of f of xi dx, f of x dx. With the same data which goes above and below 0, I am interested in only summing up the magnitudes but not the sign. What will you do? The one modification you need to do to get through this problem. Change all the negatives to positive. You should not do it manually. You would do it by, for example, I will write W of Ti, that doesn't change, times the absolute value of V of Ti. So that will be W of Ti is known, and the absolute value of Vi, I can just do this. And in fact, after that, it's all child's play because the rest of the formulas don't change. So if I just sum up the magnitudes, I'm getting 1472. Okay. Now I can be crazy about this. Instead of saying f of x, I will say f of x squared. What you would do is just go here, instead of just absolute value of v, you would do absolute value of v squared. Or I could have a weighting function and say I have a weighting function which is g of x, f of x dx, where g of x, I'll tell you, is e power minus x squared. You already have a weighting function. You have one more weighting function here, which is like a known function. So you should be able to make these little leaps, having known the basic formula. Okay, nothing like totally extraordinary. It's not genius stuff. It's just like one step next, one step next. Okay. All right, good. So this wraps up module 5. I would say I'm quite satisfied with the amount of stuff we finally got through. I'm going to post this right now. What I'm also going to do is to actually update this question. Maybe if you give me time until end of today or end of maybe by tomorrow morning, I will update this question and post this so that you can start working on your quiz. And the quiz is due by Tuesday, 11:20 a.m. Upload it on Canvas. So you get Friday, Saturday, Sunday, Monday until Tuesday morning to work on this. Okay, so I'll post this as soon as I can, no later than midnight to something. Yeah.
On the bottom.
Which column? Half width times the sum.
This case, what's the width?
Width is 0.08. So
Oh, so
yeah, the same thing that we use throughout. Okay, thank you.